Good afternoon. Welcome to the final presentation in the Spring 2026 Sustainability Research and Practice Seminar at Westchester University. Kind of a bittersweet day because Wednesdays are, at least for me, one of my favorite times of the work week to get to hear from researchers at Westchester University, students, staff who are applying principles of sustainability to the work they do. And then happily, we have guests come and visit us and tell us about their work from time to time, as we are fortunate to have today. My name is Bradley Flam. I'm the director of the Office of Sustainability here at Westchester University, and we are proud to host this program of presentations with our colleagues in the Office for Research and Sponsored Programs and the Sustainability Council's Scholarly and Creative Activities Committee. As I said, this is the final presentation, the 11th of this semester. We will take a break until the fall semester, but please plan to join us again in the fall. Even if you're graduating, you can always log on to our presentations. They're always presented in a hybrid format. So without further ado, I want to pass the podium to our invited guest, Mr. Dan Spracklin. Please join me in welcoming him to Westchester.
Thank you. As Brad said, my name is Dan Spracklin. I am the founder and CEO of SoMax Circular Solutions. And I'm here today to talk to you about relatively little known process called hydrothermal carbonization. It's a mouthful, so I'll often refer to it as HTC. We'll start off with a little history lesson. Hydrothermal carbonization was first discovered in 1913 by a Nobel Prize German chemist, Dr. Bergius. He was looking to a way to create artificial coal. There are papers going back into the 1930s in the US and the Midwest looking at the same process. After World War II, the technology sort of fell out of favor and sort of got lost to history. It was rediscovered in 2006 at the Max Planck Institute for Colloidal Science in Potsdam, Germany. At SoMax, we got involved in 2014, so about 12 years ago. And we actually partnered with Villanova University School of Sustainable Engineering. It's a graduate level program that brings across diverse folks with perspectives on electrical, chemical, engineering, and focuses on real world problems. My background was I own a septic services company. I don't have a science degree. I have a degree in English, but I know enough chemistry to be dangerous. But by all means, I have experts for that, chemical engineers and such. We did about 8 years of research and development. We published 9 research papers on various aspects of hydrothermal carbonization. In 2018, I formed and founded SoMax to commercialize the technology to bring it out of the lab and focus it on real world applications. And we've had some successes in the past. In 2019, we were a finalist in the manure challenge. That was a way of looking at valorizing manure from confined animal feeding operations. We were also awarded the first design build contract for the first commercial HTC plant in the United States. That's located nearby in Phoenixville, Pennsylvania at their wastewater treatment plant. And then in 2021, we were the grand prize winner of the Water Resource Recovery Prize presented by the Department of Energy. This was looking at technology that could be implemented across the country at medium to small wastewater treatment plants. So if you haven't picked up by now, we're going to talk about number 2. Probably one of the most critical infrastructure we have in modern society is wastewater treatment. How do we handle wastewater? And the traditional process has been to separate the solids from the water, treat the water, and then the solids had been applied and disposed of in one of 3 ways. The first one is through incineration, where they're burning it. The second one is they do landfill. So they put it in the landfill, and it's obviously organic. So depending on how that landfill is managed, it's going to valorize into CO2 or to methane. And then the third and most common practice was land application of biosolids. Land application was seen as a way of recycling nutrients. So the body doesn't really absorb a lot of all the nutrients that you take in. So there's an excess of nitrogen, phosphorus, calcium, and other nutrients, micro and macro, that were basically returned to the soil. And that practice was started in about the 1930s. Come a long way, society in the 1930s. So we have developed things like plastics, we've developed chemicals, we also have developed pharmaceuticals. So those are the three main emerging contaminants with the practice of recycling biosolids through land application. Those have some modern complications to the process. The thing is, like with these new chemicals, PFAS is the big one on all the rage today. These are forever chemicals. What happens, you apply this to land, you grow animal feed on that land, that plant takes up that PFAS compounds, they get fed to animals, and then all of a sudden that side of the milk you're drinking with your cookies has a dose of microplastics in it, or it has a dose of PFAS forever chemicals, or things like estrogen or acetaminophen, things that you're not taking that don't break down in modern wastewater treatment plants. So that's a bit of the history of SoMax, and the problem we're trying to solve is how do we recover our value from something that is deemed waste, something that no one really wants to talk about, but everyone contributes to the problem by going to the bathroom. So we have commercialized hydrothermal carbonization. A little bit about what it is. The easiest way to think about it is a pressure cooker. So you can take any organic material, whether it's waste from animals, whether it's organic debris from agriculture. So think corn stover when you're growing crops, the leftovers, human waste, obviously, but food waste, anything that was ever organic, was ever alive, can be processed through hydrothermal carbonization. The process itself is pretty simple. We just heat up the material in an aqueous environment to between 180 and 220 degrees Celsius. So for non-engineers, it's about 350 Fahrenheit to about 450. So what you would bake a frozen pizza or cookies in your home oven. We're not talking about extreme temperatures here. In that process, we also put it under pressure. And when you put an aqueous solution or water under pressure, it doesn't valorize into steam and escape. It actually goes into what's called a subcritical state. And that subcritical state is key. It acts as a reagent. So we're using this water as a reagent to trigger these chemical reactions to occur. And when that happens, you end up with a solid, technical term is hydrochar. Easiest way to think about it, if you're in Europe, they call it biocoal. Bio meaning organic in Europe. But yeah, it mimics the natural coal formation. So instead of taking hundreds of millions of years to produce, you can actually do this in half an hour to 4 hours in time. Depending on the material that you're dealing with, so a more cellulosic type material, you'd be more on that higher end of the temperature range and on the retention time for about 4 hours. So we did a lot of work with Diageo, which is one of the world's largest alcohol brands. So we worked with their beer, brewery spec grains, and distillery spec grains. So the way that you make any whiskey or vodka, a lot of times you're using grains, you're fermenting them, you're making beer, and then you're distilling it out to make your alcohols. In that process, biomass, these grains are a waste material, a waste product that are either land applied or they're fed to animals like cows or pigs. The challenge is that it's a wet material. It's very expensive to truck anywhere or haul anywhere. So you're really limited to your local farmers coming and picking it up every day. In this process, we actually created that hydrochar from both brewery spec grains and distillery spent grains and created an advanced biofuel. We did a project in a distillery in Tennessee where we could take their spent grains and we could meet the thermal demand of the entire distillery with their own waste product. So that would lower their emissions of the process by about 98% reduction in carbon dioxide emissions. Anyway, in the HTC process, again, anything organic can go in, you apply heat and pressure, you separate out, you get two products coming out. You get the solid product hydrochar, which again is like a coal, and then you get the liquid product, we call a biosolution, but it's going to be rich in organic acids, it's going to be rich in nitrogen, and so it has a lot of different uses. It can be used as a fertilizer. It can also boost biogas production, so that liquid could actually go into an anaerobic digester and even produce additional energy in the form of biomethane. So very brief overview of the process, but really it's pretty simple. Like I said, the easiest way to think about it is like a pressure cooker. So in that pressure cooker, a lot of chemical reactions occur. Do we have any chemical engineers in the room? Engineer. Okay. So for the lay people, I'll give you the overview. Basically, what we're doing is we're taking larger molecules, we're breaking them apart into smaller compounds, we're polishing off the edges, and then reassembling them into a more stable compound. This happens, like I said, in nature over hundreds of millions of years, but the mechanisms are primarily here: hydrolysis, decarboxylation, dehydration reactions, and then condensation reactions. So there'll be a quiz after this presentation. I'll expect you all to be able to memorize the chemical formulas. So when we're applying this to biosolids, it has some significant benefits. The first one is it reduces the mass of biosolids by 75%. Biosolids are typically very troublesome material to handle. It's very sticky. It's difficult to dewater. And again, transportation distances increase the price. So in the local area, we're seeing municipalities see a 50% increase in disposal costs basically every 3 years when the contract is renewed. So you have some municipalities spending upwards of $150 to $200 per ton. And these municipalities are producing tens of thousands of tons. So you have an exposure here or an expense that reaches the millions of dollars a year in annual processing costs. By doing that chemistry on the feedstock material, we change the characteristics of the material. So sewage sludge is notoriously difficult to dewater. If you dewater it to about 25, 30%, that's the gold standard. You're producing what's colloquially known as the industry as a cake. The reason for that is it represents like a moist chocolate cake. That's the consistency of the material. Most of the water is held interstitially within the biosolids itself. And through HTC, what we're doing is we're ripping apart those cellular structure, releasing the intercellular water, and then actually creating a hydrophobic shell. So we are improving the dewaterability of the material, increasing its characteristics. In addition, through that mass reduction, we're actually increasing the energy density and the carbon concentration of the material. That allows for multiple uses we'll get to later in the presentation. In addition, we are eliminating all of our pathogens. So coming out of our process with those conditions we're subjecting the material to, there are no viruses, there are no pathogens, there's no E. coli or anything like that. In addition, we're able to reduce 95% of all pharmaceuticals, remove them from the process. The way we do that is think of like acetaminophen, aspirin. We're breaking apart that chemical bond and producing its constituent components, so carbon, oxygen, nitrogen. In addition to that, we are also eliminating all microplastics in the material as well. As a side note, we just published a white paper last month where we have spent time working on PET plastic bottles. So think of water bottles. You're able to put those water bottles into an HTC reaction and break them back down to their monomers. So true chemical recycling of plastics. Basically, breaking it down into terephylactic acid and ethylene glycol. You take ethylene glycol and terephthalic acid, you put them together under extreme heat, you're producing PET. So it also allows for chemical recycling of inorganic materials like plastics. But those are destroyed, removed from the process. And then PFAS. This is the big hot topic of recent. So you see neighboring states, Maryland and Virginia, have put bans on land application of biosolids if their biosolids exceed a certain threshold of PFAS compounds. Now, PFAS represents 50,000 chemical structures, but really there's two main ones and two main branches. PFOA, which is a carboxylic head, so it has a carbon head, and a PFOS, which is a sulfonic head, which has a sulfur head. The carbon fluorine bonds are the strongest bonds you have in chemistry, so they're very difficult to break down. That's why it's a persistent, or hence known as forever chemicals. There's nothing in nature that will break down those bonds. We're able to reduce that load in the biosolids from biosolids to hydrochar. So what does it look like in practice? This is an overview schema of the plant in Phoenixville. Starting on the right-hand side, you have a storage hopper. So the material gets initial dewatering to about 15% solids, and then gets put into our system. The storage hopper allows us to operate in a 24-hour basis, continuous basis. The wastewater treatment plant only has one shift. So at 3 p.m. every day, they're gone. There's no one at the plant. They're loading up this hopper so we can operate autonomously overnight and process all the material where they're sleeping. So this hopper then feeds into a hydraulic piston pump. That piston pump then delivers it through this blue line into our heat exchanger. We're able to recover 75% of all the heat put into the system through this heat exchanger. So it's a very efficient process. We use about 1 MMBTU per hour, in this case of natural gas as our heat source. What does that mean? An MMBTU is about $6 of natural gas. So $3 an hour of natural gas to run this process. The heat exchanger brings the material up to about 150 Celsius. From that point, it leaves the heat exchanger and goes into the red line. And this is our heaters that heat up the material to reaction temperature. In the case of sewage sludge, we're at 180 Celsius, 350 degrees Fahrenheit. From that, it gets put into the reactor and then has a residence time at 7 gallons per minute. The flow rate has a 3-hour retention time in the reactor. This is more than enough time to transform biosolids. Technically, you only need about 45 minutes to an hour to transform biosolids. The longer your reaction time, the more quality and characteristics you have in the hydrochar, the more fixed carbon you have, the higher surface area, the higher porosity. In this case, one of the unique things that we've done is we've disassociated heating with retention time. So there's no direct heat within our reactor. It's basically an insulated enclosed vessel that whether we process it for 30 minutes or 3 hours, it requires the same amount of heat input. So we're able to hold that reaction a lot higher and longer without the use of any additional input heat. From the reactor, then it goes back and it exchanges back over to the heat exchanger to cool down. From there, it goes into this buffer tank. So this buffer tank is working continuously in sequence with this press. So this press is how we dewater our material. Everything prior to this buffer tank is running autonomously at that flow rate of 7 to 10 gallons per minute. The press operates in a batch mode. Every 2 hours, it will produce a batch of hydrochar, dewatered hydrochar. So as you can see, it's a pretty simple process. I like to explain to folks that we're really just talking about pumps, pipes, and tanks. So there's nothing new here. All the ancillary products are off the shelf and have been proven in industry for decades. The only thing that we've done is through the design here, and then we have proprietary anti-fouling technology in the heaters that we've developed and patented. That's the only patented thing on this whole process. In this, if you took away all the containers and everything, what you're looking at is really it's two miles of 2-inch carbon steel pipe. And that's all the process is. So nothing exotic in this whole process or setup. What does it look like in real life? These are pictures from our plant in Phoenixville. On the left here, you'll see this is our reactor. On the right is our heat exchanger. In the foreground here, this is the storage hopper. This is a 60 cubic yard, so it's pretty big. It's about the size of 6 dumpsters put together. You have your piston pump here, and then in the background here with all the insulation, you can see those are the heaters. Again, another visual. This is the large hopper. The heater system here that heats up the material. And then again, from the looking in back, on the right-hand side, a reactor, on the left-hand side, the heat exchanger. And then this that looks a little bit like a subway car, this is the press. This is a Booker press. This has been used in Europe for about the last 40 years. It owns 90% of the juice industry. So all of your apple juices, orange juices are all made through this press. It's very efficient. It is a hydraulic piston press. So when you take away the exterior, it looks like a giant juicer on steroids that you may have in your kitchen, except just using your arm to press out the material. This uses a hydraulic ram to press the material, and you get some pretty significant operations. So one of the things that we do is we're able to achieve 50 to 60% total solids coming out of this press without the use of any polymers. So polymer use is another big thing in wastewater. Sludge or cake does not want to coagulate together. You have to introduce polymer together to come together and to agglomerate in order to dewater it. Here we don't use any plastics, so we're not putting plastics into the biosolids that we're putting into our land. We're also able to capture 99% of the solids in this process. Yeah, it is a pretty cool system. Dewatering device. Coming out. This is what hydrothermal looks like coming out of the press. So you can see it looks more akin to coal or dirt, and you can see some of the steam coming off of it. 95 to 100 degrees Fahrenheit as it's coming out of our press. So with that, you now have hydrochar. Hydrochar, what can you do with it? You have a variety of different use cases for it, highly dependent though on the feedstock material. So when we're talking about biosolids, this is the most contaminated feedstock that we use. Again, it has chemicals in it. It's got anything that comes down your drain, PFAS, microplastics, and pharmaceuticals in it as well. So with sewage sludge, we like to say you can either burn it or bury it. Burning it, meaning you can do a process called gasification. You create syngas, and you can use that for energy production. So at Phoenixville, if they were to bring in the excess capacity that they have in that system with food waste and produce the hydrocharge, if they gasify it, the wastewater treatment plant goes from the largest consumer of energy in the municipal portfolio into a net energy producer. It would produce 150% of its energy demand. Wastewater treatment plants are one of the hardest things to get put on renewables because they operate 24 hours a day, 365 days a year. So with the intermittency of solar or wind, you need a lot of wind, you need a lot of solar, and you need a lot of energy storage in the form of batteries. Here, they're making their own fuel to run their own treatment plant, and then that excess energy goes out to run stoplights, streetlights, city hall, what have you. It's extra energy for them. And they're eliminating about, like I said, upwards of millions of dollars in expenses, annual expenses doing this process. Burying it, you can put it into longer term construction type materials. So you can put it into bricks as a replacement for sand, and you're effectively sequestering that carbon. With HTC, we capture about 90% of all the carbon dioxide in the feedstock material to the end product. So only 10% of the material is lost either to the liquid phase or to an off gas. So we off gas about 4% of the carbon that comes in, off gases in CO2 as that part of that decarboxylation reaction. We're actually creating CO2. Comparing that to, say, anaerobic digestion, you're about 50% carbon efficiency. And again, we're at 90% carbon efficiency with HTC. If you're composting your material, composting is about 10% carbon efficiency, meaning 90% of the carbon in that food waste that you're composting is going to valorize into CO2 or into methane, depending on your composting method. So it's about 9 times more efficient than composting, about 2 times more efficient in carbon capture than anaerobic digestion is. When you take in other materials, so talking about the distillery spent grains, those actually create a almost ideal biofuel for energy production. They can also be used as a replacement for coke in metallurgy, so making steel. So you're replacing anthracite or coke that is a fossil fuel with a renewable biofuel. And some of that carbon gets donated to the steel, hence the term carbon steel. And that carbon is now sequestered for millennia. There are other cellulosic type materials. So hemp or cannabis, you can take that material, the waste material of that process is called BASC. You can take that in a one-step process, put through HTC, and now you've made supercapacitors for energy storage. University of Kentucky just came out with a paper last week where they took the same distillery spent grains we were making into a biofuel. They turned those into supercapacitors for energy storage. So again, there's a lot of different applications. It's a bit like choose your own adventure, but it's highly dependent on the initial feedstock material that you're starting with. So to compare hydrotar to coal, which a lot of PR people say don't mention coal, it's got a bad name. It's the most apt comparison. So whereas coal took hundreds of millions of years to form under the Earth's surface, again, we're processing it in a matter of hours. And in coal, you have basically four ranks of coal. You've got lignite and subbituminous, which are the lower ranking coals. This is primarily what's used in energy production. These are dirty coals that produce a lot of soot, and produce a lot of CO2 emissions, but they do have an energy factor. As you can see, hydrochar from sewage sludge, we are in that subbituminous range of energy density. So again, taking a coal-fired power plant, displacing the coal, replacing it with hydrochar from sewage sludge, which there's an abundance, you can effectively negate and have a carbon neutral power plant at that point because all of the carbon, again, is biogenic in nature. If you do food waste, you increase the energy density, so you're getting into the bituminous range. And then if you use, say, like those spent grains, those biofuels we were talking about, so they have 36 megajoules of energy density, which is about 6 megajoules higher than anthracite coal, which is the king of solid fuels. It has 1% ash content, zero heavy metals, zero contamination. That's why you would be hard pressed to design a better solid fuel than hydrochar that is derived from spent brewery or spent distillery grains in that process. And again, these are made in hours versus hundreds of millions of years. And again, it's a net zero carbon emission factor when you're consuming hydrochar versus fossilized coal. Sort of recycling today's carbon is a way to think about it. Yes.
When you say fixed carbon, is that carbon bound in carbon rather than nitrogen or oxygen?
Yes, it's fixed carbon. It's recalcitrant depending on its structure. So not all carbon is the same, not all carbon structures. That's why you can get coal and you can get diamonds and you can get graphite. So the fixed carbon is more along the lines of the graphitic type structure of carbons than say a liable carbon, which is allows you to have basically there are hydroxyl groups on the end that allow bacteria to come in and form new compounds, borrow some of the either hydrogen or oxygen atoms of that hydroxyl and form a new compound. So talking about PFAS, again, this is the hot topic of the days. We're able to reduce 70% of all PFAS compounds in there, primarily coming from the complete removal of PFOA. PFOA, again, is a carbonic head forever chemical. That carbon head essentially gets destroyed in the process and eliminates the rest of the long chain carbon fluorine bonds. It's basically, I don't know if you've ever seen those glass structures where it's like a teardrop. and you can hit a hammer to the head and hit it as hard as you want, and it will never break. But if you go touch that tail, the whole thing shatters. Similar sort of concept here with PFAS compounds. Now, with the sulfonic heads or PFOS, we see about a 2/3 reduction in that material because the sulfonic head is a more recalcitrant to the chemistry that we're dealing with here. But overall, you're seeing about a 70% reduction in forever chemicals. What we have seen, we have a white paper coming out in the next couple of months. We've been working with the NREL, the National Renewable Energy Lab, to look at this specifically because it's very difficult to identify and extract these PFAS compounds from the organic matrix of complex organic matrix of hydrochar and of sewage sludge. So sampling and measurement is a very difficult thing right now. We actually have developed some new protocols for sampling with NREL that hopefully the EPA will start looking at. But the idea is, again, with these land application bans in Virginia and Maryland, it's a certain threshold. So if your biosolids are testing at more than 25 parts per trillion of PFOA or PFOS, you can no longer land apply it. You actually have to remove that material as hazardous waste. With this process, you get a 75% reduction. You could be at, say, 26 parts per trillion, and now you're down under 13 parts per trillion. The other thing that we see in our work is we're seeing the bioaccumulative PFAS compounds. These are forever chemicals that get into your body, you ingest them, and they never leave your body. So they bioaccumulate and they can cause health issues. We're taking those ones that we can't destroy, we are taking the longer chain molecules and breaking them down into shorter chain molecules. Those shorter chain PFAS combos, though there's no evidence today that they bioaccumulate, so they will pass through your body. So you're reducing the load to the environment and you're reducing the impact on human health as well. Again, we're not destroying them completely because in order to do that, you have to be at very high temperatures, about a little over 800 Celsius to do that, and you have to maintain that temperature. A lot of times when you're incinerating them, for example, all you're doing is transforming those PFAS from the solid, now they're airborne. And that's why you see PFAS literally all over the planet, from the top of Everest to the South Pole, where PFASs are not manufactured. So that's a little bit of the intro. I've got plenty of other slides if you want to get into anything, but I thought I'd leave the last 15 minutes or so for some question and answers. Yes.
Is all of your waste material used to power the plant? Or is any of it applied, as you mentioned, for agriculture? What also do you do with the spent liquid?
So the spent liquid actually goes back to the treatment plant and gets treated just like all the wastewater does. The municipality here in Phoenixville doesn't really have any appetite for getting into fertilizer sales. And again, these decisions were made years ago. No one predicted that where we'd be with fertilizer prices right now. But really, municipalities, think about it, they're in the business of providing services. They're not in selling products. They're not making profits, right? So they just say, hey, we'll treat it here. We got the infrastructure to do it. In a private enterprise, you would take that process water, the biosolution, and you can put it through, say, a secondary process like vacuum distillation, and you can actually produce ammonium sulfate. You add in sulfuric acid, you produce ammonium sulfate. Ammonium sulfate is a widely used fertilizer in the turf industry. So think golf, think of turf farms. It really grows grass very well. So it's a ready market material for it. You'd have an outlet for that. You can also recover some precursor compounds. So the way that the chemistry works, anything that's soluble will go into the liquid phase. That's why nitrogen goes over there in the form of ammonia. You also get precursor compounds, organic acids like levenic acid, which goes into a lot of plastics productions in modern petrochemical infrastructure. So you can get these precursors out of it as well if you want to extract the total value. But if you're at a wastewater treatment plant, you got a whole treatment plant set up, we just put it through there. At Phoenixville in phase 2, they're discussing putting in the power generation. Right now, we don't have it in. And the primary reason for that is trying to get an interconnect to the grid. In PGA market right now, you're looking at a 7 to 10 year wait list. So if they wanted to put anything back onto the grid to power their streetlights, it's a decade before they can get connected. So a little bit of red tape there to get through. Right now, we're in really proving the product. So we have partnered with LSU. LSU is doing field trials with the hydrochars as a land application. So last year they did pot trials. Now they're moving to their field trials in their farm. The big finding from their pot trials is that comparing the land application of sewage sludge or biosolids with hydrochar, you see a 70 or a 95% reduction in nitrous oxide emissions. You see a 70% reduction in methane and carbon dioxide emissions from the hydrochar. Again, to your point earlier, that liable material, it requires bacteria to interact with it to release it. So it actually acts as a slow release phosphorus fertilizer, reducing also use of eutrophication of waterways. So there's not as much runoff because you're not applying it and it's raining and running off into the streams. We're also working with the construction industry, putting it into concrete, and then also putting it into bricks as well. So now you're talking about carbon sequestration that can be done on a massive scale across the country with technology like this.
What's the mix on how much from Phoenixville, how much of the solid product is going to one application or another?
So the thing is, we get a roughly 75% mass reduction. So at Phoenixville, that system is designed as 5x what they actually produce on site. That allows them to be an importer and charge a gate fee to other municipalities in the area. So if you think of where Phoenixville is on the Schuylkill River, if you take 8 miles of the Schuylkill River, you've got 14 wastewater treatment plants right there serving Chester and Montgomery County, all producing biosolids. So those will all come into more of a regional play at Phoenixville and get processed. Right now, we're waiting for DEP to give us the final permits to allow them to import that. Long way of saying we're only producing right now about 600 tons per year of the hydrochar. So the vast majority of it is going into these different attributes. I'd say percentage-wise, 70% went to LSU, 10% into the concrete industry, and then the remainder into various other applications.
You said that biochar is porous.
It is. It's not as porous as biochar. So easiest way to think about biochar and hydrochar. They're cousins, they're similar, but they're not identical. So biochar is more akin to charcoal that would use on a grill, right? And it has high porosity, high surface area. Hydrochar is more akin to coal, where it has lower porosity, lower surface area, but it's higher energy density.
That's the one from spent grains.
It's from any of this process. Hydrochar is more akin to coal. To produce biochar using a process called pyrolysis. So basically, you're burning something in an inert environment to create that biochar. You're burning off all that liable material, and then you're left with essentially fixed carbon at that point, and inerts, so ash, minerals, things like that. With HTC, there's no combustion in this process at all. So we do have a little bit of off-gassing. Like I said, about 4% of the carbon comes in and produces the CO2. That's released when we open up the press. Otherwise, it's a closed system and there's no combustion process here. So it's a difference in how you create those two materials. Biochar and hydrochar always get sort of confused, but they are distinct differences.
How big are the pores? How porous is it?
It depends on the feedstock material. So if you're starting with like a hardwood, you can get very porous material. The other thing with hydrochar, there's this, to get very technical, there's a secondary reaction in this process, and you're creating carbon spheres, and those carbon spheres actually get into the pores and clog the pores. It's interestingly enough, if you take that processed water afterwards and you leave it alone for 96 hours, you actually get self-accumulating and aggregating carbon nanospheres. So a lot of those materials are being looked at for medical applications. So things like imaging, and you can put those carbon nanospheres, and these are at a very, very small level, almost imperceptible to the eye, using those for different applications. But you don't have to do anything. You take the processed water, and from a chemistry perspective, it's pretty cool. It self assembles into a carbon nanosphere.
Does that happen at room temperature?
Yep.
Or-
Room temperature. And again, it doesn't require agitation or anything. You can just set it in a jar. You leave that jar alone for 96 hours, you'll develop some carbon nanospheres in it.
A municipality has a lot of responsibilities, one of which is helping to manage wastewater. Purely from sort of the financial perspective, is Phoenixville spending more on their wastewater treatment with this new technology than they would if they had just stuck with traditional technology, or are there cost savings that?
There are cost savings. So operationally, there's cost savings in reduction in the amount of polymer that's used. So they order polymer in totes. Those totes run anywhere from, depending on the polymer, from $2,500 to $10,000 a tote. They typically go through one tote a month. Now we're reduced that by about 50%. So there's savings there. There's also savings in the disposal cost. So if you were paying $100 a ton to dispose of this, and now you're selling this hydrochar to the construction industry for even giving it away, it's $100 per ton saving. So the economics of a process like this depend on the savings and the delta of savings in that disposal cost. And we've seen it. So Phoenixville was around $65 a ton. In Upper Marion, for example, it's $165 a ton. So there's $100 per ton disposal cost delta in roughly 6 miles. So it's highly variable. So the higher cost is the higher savings here. And again, what are you spending on energy? But the challenge is you have to build the plant or the factory before. So there's an upfront capital investment in the project. This project at Phoenixville will pay itself back in 6 years. And then over the 25 to 30-year lifespan of the project, of the equipment, they're looking at upwards of $20 to $25 million in savings that go back into the general fund that wouldn't be spent on just disposal.
And is the technology fairly scalable so that a city like Philadelphia with 1.5 million people could do it the same way that a smaller plant serving a population of 10,000?
Yeah, so scaling up is actually easy for us. What we do is we basically just put in trains. So instead of us designing a larger reactor custom to that site, we just put in, multiple trains of reactors. So you may have 10 to 15 to 20 of these trains at, say, Philadelphia, where in Phoenixville you only need one. So this train will actually process, to give you some sort of scale, the human waste of around 100,000 people. It will process 25,000 wet tons per year at 15% solids. We can go up to about 35,000 tons per year if we increase that flow rate. So there's two ways to increase the throughput. One is to increase the percent solids, and the other one is to increase the flow rate. So it allows us to kind of move up and down. The harder challenge is actually going into, say, rural America where there's 1,500 people. And the reason for that is not our technology per se, it's the press, it's the ancillary equipment. So to give you an idea, this pump right here you see in the foreground, that's a $250,000 pump. So whether I'm putting 35,000 tons through it or 3 tons through it, that pump still costs the same. So that's where the challenge is in scaling it down, is more economics than it is anything else. Yes, bud.
Do you foresee this becoming like really popular? It seems like it's relatively costly, even though there's a large upfront cost, and then the economic or the environmental pros of it. Do you think it's going to become popular?
Well, I would love to see it become popular. I mean, that's one of the reasons I got obsessed with this about 14 years ago. One of the challenges is that wastewater treatment and municipal operations is probably the most conservative industry you've ever come across because they just can't afford to get it wrong. They can't just say, oh, no, we can't treat wastewater anymore. It's not an option. And so a lot of the feedback I get is, come talk to me when you've got 100 of these plants, 200 of these plants, 1,000 of these plants. Yes. So we have one plant right now. We have 4 in the works. But for us to get to that scale, to give you an idea, in the United States, there's over 15,000 wastewater treatment plants that are small to medium size. Will we get all of them? No. But you can start to set up things. And the other thing would be thinking about this not just as a wastewater treatment, but also as an organic recycling process. So again, I can take food waste in 2 hours. I have hydrochar on the back end of it. Whereas again, if you compare that to, say, anaerobic digestion, you're looking about 30 days. So in order to have that residence time, you're building these large tanks that are multi-million gallons in size. Composting, is a great process, but it takes time. Where you're at basically depends on whether you can do it year round or not. This is something you can do year round. You can do all that. So I would like to see this as more of an organics recycling play, and I'd love to see people be as familiar with it as they are, say, composting. Right? Everyone knows what composting is. You can do it in your own backyard. HCC you probably can't do it in your own backyard because of the pressures complicate things a little bit. Which is why you can see in all of our valving here, these are all safety measures and valves that we can release pressure if we need to. The nice thing about this, and one of the reasons why Phoenixville decided to go down this route, is they had anaerobic digestion. Their anaerobic digester is so inefficient that they actually spend about $80,000 a year on natural gas to heat the digester to burn the biogas that they're producing. I asked the public works director if it would just be simpler to burn that $80,000 in cash. So the other thing is they had an incident in the early 2000s where an employee did something they shouldn't and caused an explosion in their digester. The council wanted nothing that could ever explode. This process was not doing combustion. It's not going to explode. The biggest thing you'll see here is like a tea kettle. You'll see a pressure relief come out. You'll see steam come out once it touches that ambient air and it loses its pressure. But great question. Yes.
Is there any way to integrate like specific parts of this into existing systems to kind of reduce the burden on like municipalities to just kind of like introduce completely new systems?
It is. We're gaining some traction in traditional sanitation. So one of my concepts is you put these facilities at landfills and just separate out all the organics. You extend the life of the landfill. You reduce the emissions coming from the landfill. You reduce leachate. You reduce PFAS contamination, everything else. But again, very conservative industry. Tell you've got 20 years of track record. The quote I got from the executive at Waste Management was, we like to be cutting edge, but not bleeding edge. Where you're seeing this take more hold is in Europe, and specifically in the EU, because they have regulatory drivers of this. They have a carbon market. In the US, there is no carbon market, it's voluntary. They also have a requirement to recycle phosphorus from sewage sludge because they import 100% of their phosphorus, so it's a national security issue. HTC, again, we retain all that phosphorus within the solid. And so again, it acts as a slow release fertilizer. In the US, we don't have that issue because in the US, we sit on the 3rd largest reserves of phosphorus on the planet. It's called the state of Florida. State of Florida is an entire phosphorus rock, basically. So we don't import phosphorus from Morocco or from China, whereas the EU, they have those drivers. So you're seeing a lot more development in the EU and in Asia than you are in the US. One of the other challenges that we have is, again, economics. So twice a month, I get someone reaching out to me from sub-Saharan Africa saying, hey, we have this problem with sewage, we have no infrastructure, can we put this technology there? The problem is we can't compete with free. So if you take someone like South Africa, for example, South Africa disposes of all their sewage sludge by dumping it in the ocean for free. Now, it costs them monetarily nothing, but you can talk about environmental issues and anything. But then when you could say, oh, now you're going to have to pay, the equivalent would be about $40 per ton to process this material. The economics just aren't there in places in the developing world. Yes.
The material that you put into your process, is that converted from the primary or after screening?
It's after screening. So they actually at Phoenixville, they screen it first, goes into their settling tanks, then gets pumped over to the building, and then it goes through what's called a muffin monster to get any rags or anything that got through, and dematerialize that. With HTC though, we don't really worry about contamination. We don't worry about plastic straws or anything like that getting into it because we're going to break that down to its monomers. Whereas if you're looking at, say, anaerobic digestion in a biological process, any contamination is a big issue. Not for us because we don't use biology, we use chemistry. Chemistry works. It works everywhere you're on the planet in as long as you have the right conditions.
Dan, we're just a little after 12:50, and we usually pause right now because some students and faculty have to get to other classes by one. So if you do need to leave now, please feel free to do so. If you have a few more minutes and there are more questions, those of you who still have questions, please plan to stay.
So going back to your discussion about integration, so here, if you already have an anaerobic digestion plant, we can integrate with that, and we can actually increase more biogas. That additional biogas that we produce actually goes to drying the hydrochar material, so that you can put in a combustion or waste energy type process there. So yes, it can be integrated. Hydrochar can be integrated into waste energy facilities. We're looking at a plant in Michigan that the wastewater treatment plant's right here. The waste energy plant is across the fence. So all the hydrochar would just go across the fence to the waste energy facility. Yes.
I'm sure this depends a lot on geography. So, like in southeast Pennsylvania or Pennsylvania as a whole, what are the relative, amounts of feedstock if you compare, waste grain from either distilleries or breweries, sewage, or food waste?
So I don't have a number for you, but the numbers are going to be enormous because you can also add in like CAFOs, confined animal feeding operations. So think of all the poultry farms in the Delmarva Peninsula. For example, they can't apply chicken litter in Delmarva to the land anymore because there's
waste. When I was in Virginia, we had people from Purdue trying to because or chicken waste. Yeah.
So chicken litter, turkey litter, southeast Pennsylvania. You got a lot of food manufacturing in Lancaster County. I worked with DEP in the state, and the biggest food waste production is actually in Allegheny County over in Pittsburgh area, because that's where the vets, Heinz, and all of those factories are. So when we think about food waste, we may throw out 10 pounds, 20 pounds. They're throwing out hundreds, thousands of tons on an annual basis. So the volumes are enormous. And again, anything organic that that was ever alive can be processed through this process. We just fine tune the temperature and retention time, and we do that. The other nice thing about hydrothermal carbonization is that it's a family of technologies. So like all fossil fuels were made, got covered by the earth, applied pressure, applied heat. So with HTC, if we turn up the temperature, turn up the pressure, you get hydrothermal liquefaction, which produces a crude oil. You turn up the temperature and pressure even higher, you get hydrothermal gasification, which produces syngas, just like you would. So again, you're getting coal, you're getting oil, and you're getting natural gas. You can replace all of those within the hydrothermal treatment family of things. HTC is the lowest. It's lowest temperature and process intensity. It also, you have a ready to made product right there. So if you're doing HTL, hydrothermal liquefaction, you have a crude oil that needs to be refined. So you have an intermediate product, whereas here you have a useful end product right there at the factory floor, if you will. Yes.
What about the energy inputs to produce the high temperature pressure? Like,
That typically comes from, you can make a self-containing loop where you can produce all the energy. Or like in the case of Phoenixville, there was literally a natural gas line that ran there. And so we just tapped into that. Once that phase two comes in, they're producing their own energy. All that waste heat will run this process. There'll be no outside energy inputs. So this is a very energy positive on a mass balance basis. I have an example right here of a mass balance. So we're consuming electricity, we're consuming natural gas. If we put that to energy, we would be able to produce an excess of about 27,000 MMBTUs per year of heat and about 3,000 megawatt hours of electricity at Phoenixville. Optionality is you could also sequester a little over 700 tons of CO2 per year, long-term carbon sequestration if you were to go the Berrien route.
so I'm thinking about the factory farms for pigs down in the Carolinas. Saw the air in this. That sounds like that would be a fruitful place.
It would be, but again, what the incentives are in the United States. So you take Purdue, you mentioned Purdue earlier, or you take Smithfield. The way they've set it up is that they have basically farmed out everything to the farmers. And so Smithfield owns the pigs, they supply the inoculations, they supply the feed. The farmer is essentially a babysitter. What they've done in that contract is the farmer is responsible for all the waste. And so you have a farmer that's barely eking by. They're building these lagoons because I can dig a hole for cheap. And they store those lagoons, and then you see that's what you're seeing from the air. That's the reason, because not Smithfield's problem, not Purdue's problem. And it's just a mechanism of the way that we set up the modern factory farm infrastructure is we've left all the liability with the people that can least afford it and least know what to do with it. So change that dynamic, then you would see a lot of effort gone into addressing these problems.
We should probably finish up. It's after 1, but I have one last question.
Yes.
You talked about the return on investment that Phoenixville is expected to appreciate. You talked about how this is sort of the first wastewater treatment plant application in the US.
Yes.
Other companies that are
In North America, it's the first wastewater treatment plant. There is another plant in Mexico City that does hydrothermal carbonization of the organic fraction of municipal solid waste or food waste. But they do hydrothermal carbonization plus pyrolysis. And so they're producing biochar from wet organic waste. That's all of it in the Western Hemisphere. There are 18 plants in Europe, and there are, within the next year, there'll be over a dozen in Asia.
And you talked about how conservative the wastewater treatment industry is. You've been open in Phoenixville for a year? Something like that?
We commissioned in 2023.
And so have there been any hiccups?
Yes.
Any
Yes.
problems that
So
wastewater treatment operator, sort of watching you from afar might be saying, "Oh, this is riskier than I expected." What have been those?
So the biggest hiccup at Phoenixville was an oversight in the project development. They put it into a greenhouse that had no air movement or airflow. And so again, as we open up that press, we're off gassing. And there are odorous compounds, primarily sulfur compounds. It's not the same odor as a wastewater treatment plant. So it attracted a lot of attention. And an abundance of caution, Phoenixville shut the plant down because we were the ones producing this new smell. Um, they've now put in some infrastructure to have air movement and air treatment there to deodorize it. And so we are actually firing up again next month. We've been down for a little over a year while we were putting in this new equipment.
Okay.
That had nothing to do with HTC process or the equipment. It was actually a function of the building that we were put in and oversight and development project. So that's what they're looking at. But now that we have the odor issue resolved, it's again, show me when you have 10 plants, when you have 100 plants, when you have 200 plants. No one really wants to be the first, which is why there's a lot of credit to Phoenixville and the authorities over there that they wanted to be on that bleeding edge and pioneers, which has benefited Phoenixville. They've gotten a lot of positive PR. So they had the Swiss ambassador to the US came to the plant. There was a big shindig there. They've been reached out to by municipalities in New Zealand and Australia, talking about their process, So it has some other benefits for Phoenixville. Put Little Phoenixville on the map worldwide, from this aspect of things.
More than the blob.
I would say so, yeah. A lot of people haven't heard of the blob.
A more current.
Yeah, you gotta be a certain age to remember the blob.
Here's the blob. Ask pizza.
You could. You could.
That's it. Is that what else we had?
Okay, I just have to say that Blobfest does still happen every year and has for a couple of, I think it's been running for about 20 years now. So the Blob is making a comeback.
Yeah.
So it's blob's never going away.
Right.
We are well after 1 o'clock, so we probably should end. Can I just mention that when you and I talked, after the Swiss ambassador was here in October, I think it was.
Yeah.
You mentioned that tours might be a possibility.
Yeah.
Plant, Kurt, John, Walt, think about organizing something maybe in the fall semester. If that would work for you.
Yeah.
Yeah.
Yeah, that would work for me. We can, it just has to happen between 7 a.m. and 3 p.m.
Okay. All right. Thank you.
Thank you.